Lagrange. For an nth degree Taylor polynomial, P sub n. Or didn't you guys see your book could say T sub n? Yeah. Whatever. For a Taylor polynomial approximation, and remember Taylor could be Maclaurin if it was centered at 0, so Maclaurin, Taylor, whoever. A polynomial approximation for a function. R, which is just my error. Worst case scenario for my error is, okay, so it's not that the error equals, it's that the worst case scenario or the Lagrange error bound is. What's n plus 1 up here denoting? The next order, but specifically with f, there, it's the next derivative, right? So the n plus first derivative at, okay, so z is an x value, true? And specifically down here, I'm saying it's an x value that maximizes the error. All over n plus 1, oh, this is just the n plus 1 term, right? So everything is normal except who normally should go there? Not z, but c. Does that make sense? Normally, it would be the n plus first derivative of c. However, Lagrange says, I can't say that's the worst case scenario. I'm going to maximize this n plus first derivative and not just say at c, but instead say at z, and you can find z. Now, sometimes we're going to find z exactly. Sometimes we're going to think about the n plus first derivative and be like, I don't care who z is. I just know the worst that it could be in this interval. Now, hold on, pause. What interval did I write on Friday? I was measuring from the center x plus c, x minus c. Now, hold on, wait a minute. Is c being added and subtracted from x? No, what's c? The center. So shouldn't things be from c? Okay, so hold on, we got to change this interval, okay? This interval doesn't make sense if I'm adding and subtracting c. I did it really quick. I wasn't thinking very clearly. C is the center. C is where we're measuring from. At c, it's exact. Apart from c is where it goes off. So c is going to be my plus or minus in the sense of c plus or c minus. Now, hold on. What interval should I be looking at? C is my center. I'm going plus or minus because think error could be above or below. But x values, what's my other important specific x value? Got it. A could be above, A could be below. So specifically, I'm looking on the x interval starting or centered at C, going A above and A below. And that makes sense in the context of the problem that I am centering my function at C, I'm evaluating at A, so that's how far off I've gotten. Does that make sense, kind of? Okay, so I needed to make sure that interval was correct. Now it's okay. And we're trying to maximize the n plus first derivative on that interval. I don't have to worry about anywhere else because I'm deviating a amount. I need to worry about my n plus first derivative. So now that I have that interval down, now that our endeavor card is correct, sorry, now let's go back to our note. Sometimes this value, basically they're saying, is either hard or impossible to find, at least by hand. And if it's not able to be found by hand, then some of you might be thinking, well, what's the point of the approximation? Because the approximation is keeping us from going to our calculator, et cetera, et cetera, et cetera. What they're saying, if we get to one of these cases, and usually it has to do with trig, to be totally honest. If we get to one of these cases, we may choose the first, I know it's really awkward and sad and ambiguous wording, the first known reasonable, what's reasonable? Rational number greater than. We're going to be looking as much as is possible on this interval. But from time to time, we're going to be like, that didn't help us. We don't really know what that value is any better than we know the function value we're trying to approximate. So fine. You know what? What will sine and cosine always be between? So if our n plus first derivative is sine or cosine, if worse comes to worse, if we find something like our maximum of sine on an interval is like sine of 0.5, we'll be like, I don't know what sine of 0.5 is. 0.5 is not like 30 or 45 or pi over 2 or pi over 4. I don't know what it is. Maybe we'll just be like, 1. we might not get the decimal 4 sign of whatever our maximum sign is on a certain interval. We might just say 1. And you might be like, well, that's annoying because that's worse than the worst case. Oh, well. Sometimes if it's hard to evaluate or hard to maximize the n plus first derivative, we might just choose the reasonable, all right, fine. We might not know what this is, but we know it can't be any bigger than 1, so we'll just choose that. Okay? If we choose a number that's too large, we defeat the purpose of the error bound. But if we choose a value smaller than, if we try to approximate and we choose something smaller, then we just lost our guarantee that our approximation will fall in our interval. So what they're saying is, you don't want to go too big, but you also don't want to go too small. So if you don't know exactly what the decimal approximation or what the decimal value of an awkward n plus first maximized derivative on the interval is, do your best. Keep it reasonable, which is really awkward. It sounds like that stats class yesterday, which is ridiculous, but oh well, it is what it is. So here we go. Stats is all like, oh, just keep it reasonable. Anyway, keep it appropriate. Keep it, anyway. Some of the wording in stats is super awkward and annoying. But I like things to be precise. But stats is kind of like, well, yeah, we think. And they have like reasons and tons of algorithms and all this stuff behind the thinking. But anyway. So here we go. Let's try to figure this out and see what's going on. Suppose we use the first two terms of the Maclaurin series for ln of 1 plus x. 1 plus x, I think it's centered at, It's okay. We'll see. To approximate f of 0.1. We want a special Maclaurin so that we don't have to do all the work of f prime, f double prime, f triple prime. Sweet. So go ahead and look at your hopefully special Maclaurin series to say, who is ln of 1 plus x? Is that a special Maclaurin? Oh my goodness, it's back so far. We skipped so many FRQs. Oh, hey, it's perfect. Okay, you guys got it, right? You can tell me what it is? So ln of 1 plus x, sorry, I haven't rememorized them for this year, is equal to over 2, not 2 factorial, over 3. Wait a minute, what are we supposed to be using, though? Oh, okay, cool. So the first two terms, who is that? Isn't that p sub 2? Why am I doing that? Well, because doesn't the Lagrange error bound determine, or isn't it based on where you stop? Okay, so we are going to use that to approximate, As soon as I did this, what do I need to do here? Because the dot, dot, dot was okay. Wait, was it okay? What's the interval of convergence for ln of 1 plus x? Oh, so yeah, we would have been in trouble. I couldn't have written the equals anyway. For some of them, I can write equals because the infinite for all real numbers do converge. Others, they don't. Okay, but the approximate, now I'm good. So we're going to go ahead and approximate ln of f of 1.1. Oh, if x is 0.1, can't I plug it in and say I'm approximating ln of 1.1? Okay, so then I'm going to get 0.1 minus 0.1 squared all over 2 equals p sub 2 of 0.1. Are we good? So who is my a? 0.1. It makes sense? It's because of that 1 plus. Yeah. Now specifically, you're like, oh, this is impossible. I don't know how to do that. Well, yeah, you do. Because isn't that just 1/10? Isn't that 1/10 squared is 1/100th, and then over 2 is 1/200th? So I'm doing 1/10 minus. You're just saying, sure, go team. Minus 1/200th. Wait, what's 1/200th? That's awkward. Same thing as. Couldn't we make that 0.1 minus 1/2 of 0.01? So couldn't we make that 0.1005? Because half of 10 is 5, but it's going to move a decimal place. If you want to double check me, actually, I would feel a lot better about that. But anyway, I think that's right. Now what? Find an error bound using the alternating series error bound and the Lagrange error formula. Oh, stinks. So when the AP says error, they might be meaning two different things. That's okay. Let's start off with alternating remainder.
Wait, so why did we just do what we did? Why did we just...
Sorry, Riley. Yeah, what? Oh, because at the very beginning, use the first two terms. Otherwise, I wouldn't have known, and we would have been in trouble.
We gotta fact check.
9.5? Hold on. 1/10 times 1/10 is 1/100th.
Oh, yeah, the one with, because you have to like. That's if you add. Yeah. That's if you added.
Oh, thank you. I added, not subtracted. Thanks, Lisa. Sorry. So that'd be point. No, thanks. I appreciate it. I didn't subtract. My bad. Sorry, guys. Okay. Oh, yeah. I was subtracting. Never mind. Alternating remainder. What does that say? Remainder is less than or equal to a sub 3. Because alternating series just says, oh, it's a series. It's cool. It's next, or it's less than the next term. What's the next term? X cubed over 3, right? So I could go ahead and say, okay, R2, who am I plugging in? I'm plugging in 0.1. It's going to be less than or equal to a sub 3. So that would be my remainder is less than or equal to 0.1 cubed over 3. Aryan, go ahead.
I'm confused. Does the equation not cross series
Oh, interval of convergence. For values between.
Negative, and then it can be equal to 1. It was negative x.
Yeah, negative is not equal to because that would be a vertical asymptote. So open interval, the IOC according to our card. There you go. LNs. We don't even have to look at the ln. We're just looking at the series. And according to the series, values between will be decreasing because they'll be fractional exponents, not whole numbers.
So since the interval convergence is like non to infinity, you don't have to do limit to infinity. So alternating series is like number 1 is limit to infinity and number 2 is decrease to 0.
But limit to infinity for these values would be 0. Because if you're squaring like 1/2, cubing 1/2, like it's decreasing. Do you see what I mean? Yeah. But you're right. If it went outside the interval of convergence, it means nothing. The whole test fails. Right. Because 0.1 is. Does that make sense? Like we're not going to infinity. We're going to 0.1, which is okay because it's totally legal within our interval of convergence. 0.1 cubed divided by 3. Would be 1/1000th. Anyway, we'll stop there. You guys can get me a decimal approximation. Cool. But we're not just doing alternating. We're doing Lagrange and asking ourselves what the difference is. Because both of them say the n plus first. So what's the big dealio, right? In alternating remainder, we say the remainder of our two terms of 0.1 is going to be, well, worst case scenario. So we're going to say less than. But you could say the Lagrange error bound if you want to put it that way. The Lagrange bound, if you guys want to see the difference. This one says that the error is less than or equal to. This one says it's bounded by. That's why there's that equal. Is the n plus first derivative, which means the third derivative, right? Of z all over n plus 1 would be 3 factorial, right? All times x cubed. Not pussy. And then absolute value. Wasn't that the same thing? Uh-oh. What's the dilemma? What do we have to think about? Yeah. We can't just think about what the third derivative is centered at 0 according to our trick. We have to actually think about the third derivative and think about his max or his min. So that stings a little bit in the sense of, okay, we have to actually take derivatives. But the nice thing is, guys, isn't there a u prime a 1? So my first derivative will just be 1 over 1 plus x, no big deal. My second derivative is going to be bring down the negative 1 over 1 plus x squared. And my third derivative is going to be bring down the negative 2 over 1 plus x cubed. And I'm specifically considering this guy. I'm trying to maximize him on. Okay, let's think. Hold on. We did that whole interval thing a second ago. We're going from c, which is 0, plus a and minus a, which means negative 0.1 to positive 0.1. Well, it's not too bad because your u prime is 1. If your u prime was like an x and we had quotient rule, that would be disgusting. Ah, because that's the point of z. We're trying to maximize this guy, this third derivative, on the interval c minus a, c plus a. A is our 0.1, c is 0 because it's a Maclaurin. So 0 plus 0.1, 0 minus 0.1. Ah, that's our objective. So guys, who is this function? He's a cubic, yeah? Oh, he's a rational cubic? That's nasty. What do we know about rational cubics? We know what this guy looks like, true? Basic graphs, if I cannot take a derivative and have to do like the whole maximized process, my life is better, true? So wait, wouldn't this guy be roughly, hold on, his vertical asymptote is at negative 1, true? And isn't he negative, so he's flipped down, he's something like that? You guys agree? So who's that dude? Asymptote is still at negative 1. But he's a cubic. Isn't he going to be like a 1 over x? What does the 2 do? Stretches it a little bit. Okay, cool. What does the cube do? Makes it a little bit inwards as opposed to being outwards as far as like being more... It gets closer to the vertical asymptote, but otherwise like its behavior is the same. What's the maximum value of this guy on negative 0.1 to positive 0.1? Negative 0.1. Because my function is decreasing this whole time, right? So between negative 0.1 and positive 0.1, the maximum value would be at negative 0.1. So what does that mean? Z equals negative 0.1. So then with Lagrange, we can just go ahead and plug it in. Plug what in? Well, we're still plugging in 0.1. We could have technically done that way back here with x because our a is going in, just like we do with a tangent line. We plug it in the x spot just to do with Euler's method. We plug it in. So we could have plugged in our 0.1 way back here. But what's new is that we're plugging in this negative 0.1 for our third derivative x value. Oh, x value. So where are we plugging it in to? Yeah. So therefore, our Lagrange error bound is going to equal. We have 3 factorial. Can't we just make that 1/6? Is that cool? Okay. And then we have our third derivative, which is this guy with a negative 0.1 plugged in. So we can do 2 over, well, can't we do this? 1 minus 0.1 is 0.9, true? And then we have our 0.1 cubed. All right, calculator. I want you to get me decimals for both of these, and let's see the difference. We have our alternating up above. We have our Lagrange down below. The alternating. Ugh, what happens when you don't take your Mucinex in the morning? Okay. 0.1 cubed over 3?
Yeah.
Is what?
It's 3.3, it's just to the fourth. But it's going to be 0.0003 repeated. Yeah.
Okay. And then I'm coming back down. I know it was too fast for some of you guys. There we go. Justin, you had a question? Okay. Oh, hey, that can be 1/3. You're welcome. Made life so much better. 0.1 cubed over 0.9 cubed? Wait a minute. Isn't that just 0.1 over 0.9 cubed? Yeah. Like that? I forgot the 1/3. Well, either that or take the fourth derivative and do like the whole maximizing as far as critical numbers and
So basically you have to use a calculator for something that you can just literally find.
I didn't have to.
Okay, but you know the graphs.
But the basic graph though. Hold on, the basic graphs. The basic graphs. Because isn't this like a 1 over x that's been shifted one left? 1 over x, yeah? What's 1 over x cubed look like? 1 over x to the 5th look like? 1 over x to the 7th look like? They just get like squished in. They all follow the same pattern. What's 1 over x squared look like? Oh, no negatives. 1 over x to the 4th. 6. Sorry, I can't, my palms are in the way. But anyway, long story short, like I'm using basic graphs. Why? Because I was lazy. And I would love to say, oh, he's decreasing on this interval. So the highest is there, the lowest is there. Why? Because if I zoom in, zoom, 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 it's going to be higher on this end than that end. Zoom, 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 zoom. No, done, done, done. Okay. First one's so much better than all the others. Anyway. Yes. Yes. And the best harmonizing part is somewhat inappropriate. Anyway, coming back. Guys, how close were they? 0.0003333 and 0.0004527. They were different, but how close were they? What was this one dependent on? That it was alternating. What's this one dependent on? That's a Taylor polynomial. Wait a minute, hold on. You guys have your special series. Are some of them not alternating? Yes. So could I use the alternating series remainder theorem? No. No. But what can I use? Oh. Now, here's a very particular word that you guys have to look out for. Not only the word Lagrange, or the maximum error. Although, sorry, I have problems in my head where the maximum error just meant do the alternating and then maximize it. But anyway, yeah, just don't ask. We'll get there when we get there. Lagrange, the idea of Lagrange isn't getting the smallest error bound. It's having the worst case scenario, but at least giving you an idea of how close you are with a Taylor or a Maclaurin polynomial. So, I want you guys to, not the entire thing, let's just do A. Ponder A. Ponder A. Let f be a function with 5 derivatives on the interval 2 to 3, assuming that the 5th derivative of x is less than 0.2 for all x in the interval 2 to 3, and that a 4th degree Taylor polynomial. Wait, why are they giving me a 5th derivative if they say a 4th degree Taylor polynomial? They're maximizing it for me. We don't have to. No. Maggie said, is that my z? No. Z is an x. What is this? The function, the 5th derivative function value. We don't need to know z. We need to know what he's maximized at. I don't need to know where it happens. I just need to know what his maximum value is to plug in. So you don't always look for the z. Sometimes they give you clues saying that's the maximum. I'm like, okay, cool. I don't care who z is. I'm just going to use the max. Thank you.
I get what you're saying.
See it? So the z is when it happens. I have no idea when this happens. All I know is that that's the maximum he can possibly be. I'm going to play with this as you guys, if you want, go up and grab coffee, I think a couple of whatever goodness is in there. And then let's come back and talk about section 10.2. Take a quick mental break. I'm going to play with him. You guys grab a couple goodness thingies in the box. If you want the lemon squares, the raspberry things, whatever, they're on the bottom. All right. Put a lid on. That way we don't make a mess. And then let me play. The lemon bars are in the bottom, the raspberry things are in the bottom, the chocolate droppy things are in the bottom, the biscotti-ish things are at the top. If you're allergic to nuts, you might not want to eat anything in that box. Are you allergic to nuts? I mean, as long as you get something without, well, I'm saying there's nuts that could have come in contact, like ones with nuts and ones without. Okay. Some of it's not super sweet. No. I was thinking the biscotti would be like just lightly, like not super. E for effort. Do you guys see the Dove chocolate one I got? Yeah. Yeah. Spoiled rotten.
Why'd you say it like a question, Jake?
With a little bit of brown? A drop or two? Hey guys, can you see if that makes sense? So my A is 3. My A is 3. My interval my interval is accurate, my interval is correct. Ugh, we have to change that interval again. It's okay. We have the idea for today. My A gets plugged in. My A does not get plugged in. I need the maximize, so the maximize is 0.2, so I plug and chug and then I solve. We'll talk more about it tomorrow, but just the idea of Lagrange once again. Wait a minute. Wait a minute. Why not alternating? I know nothing about this Taylor polynomial. I have no idea if it's alternating or not. The only thing I could have done, I don't even know the terms. The only thing I could have done was Lagrange. All right, cool kids, with that. Section 10.2. Here's what I'm going to do. You guys have questions on chapter 10, yeah? Section 2. Section 2 was the Taylor polynomial, the nasty section that I went ahead and posted comments on Google Classroom. We talked about it in class, and then I posted more comments on Google Classroom. I think it was just updating the special Maclaurens, though. Remember, there were the easier ways versus the harder ways of building those Taylor polynomials. I'm going to go ahead and right now on the video, I'm going to scroll through. No, let me just do this. Do you guys want me to copy and paste the even answers and put it in the Google Classroom assignment? Does that sound good? That's easiest, right? Okay, and then I want you tonight, because you have the back of the book for the odds, and then you're going to have the answer key for the evens. I want you to come with informed questions tomorrow. Does that sound good? Because you guys, I know you got stuck on 10-2. I know it gets nasty. So let's go ahead, beginning of class tomorrow. Let's get into section 10.2 after you've seen the evens and seen the CalcChat-ish answers, because, we haven't had CalcChat in this chapter, right? So use the evens as CalcChat and then come in tomorrow with, okay, so why? Sound good? Okay. And then what did I give you? What did I pass out that you guys could start playing with the Taylors? Yeah, it's the test review. You can start playing with it if you want to see how your understanding is, if you're stuck or if you're behind on homework, etc. But anyway, does that sound good for today? Can we stop?